Okay, so now we're going to introduce the scheduling algorithms. So we're going to introduce them in terms of three main categories. The first one is algorithms that work for batch processes. So batch processes are actually background processes that do not require a lot of intervention or a lot of interaction with the user. So to schedule these processes, we can use the first scheduling algorithm, which is called first come, first serve. So the idea here is we serve processes based on arrival. So we keep track of a queue for the waiting processes. So it's actually a FIFO queue. So whenever we have a new arriving process, we add its PCB to the tail of the queue, and then we always service the process whose PCB is at the head of the queue, right? And so whenever a process is serviced, we are going to remove that process from the queue. So first come, first serve is a non-preemptive type of a scheduling algorithm because now remember we talked about the difference between preemptive and non-preemptive. So with first come, first serve, once the scheduler has chosen process P1 to run, we are not allowed to interrupt that process before it completely terminates or issues an IO request, right? So first come, first serve is fairly simple to implement and to understand. However, as we will see, it yields a fairly long average waiting time. So let's see an example. So here we have three processes, and these are their corresponding arrival times. So P1 arrived at time 0, right? P1. And then P2 arrived at time 1. This is P2. And then finally P3 arrived at time 3, right? And this is their corresponding burst time. So remember we discussed burst time. It's mainly the CPU processing time that each one of these processes is requesting, right? So P1 is currently requesting 6 milliseconds, for example, and P2 is requesting 3 milliseconds, and the last process, which is P3, is currently requesting to run for 2 milliseconds, remember, on the CPU, right? So this is their requirement. This is what these processes are requesting. And again, this is when they arrived. So assuming the scheduler is executing first come, first serve, so obviously the first one in the queue, right? So this is our queue. At time 0, we have process P1. So process P1 will start running at time 0, right? And process P1 requests 6 units of time, or 6 milliseconds. So P1 will run from time 0 all the way to 6, right? So it will run for a complete 6 units of time. So even though P2 has arrived at time 1, so P2 will be added to the tail of the queue, as well as P3, which arrived at time 3, will be added to the tail of the queue. But even though these processes arrived while P1 is executing, because first come, first serve is a non-preemptive algorithm, we're not allowed to preempt or to interrupt P1 while it's running, right? So we'll have to wait for P1 to continue running all the way at time 6, and then we remove P1 from the queue, and then the next one at the head of the queue will run, which is P2, will run starting at time 6, and P2 requires 3 milliseconds, so it's going to run from between time 6 to 9, and then we remove P2 from the queue, and finally we have P3, which will run between 9 to 11 because it requires 2 milliseconds, okay? Now, as we said, to compare the performance of these scheduling algorithms, we're going to be using two metrics, the waiting time and the turnaround time, or the average of these two criterions. So for the waiting times, it's simply as the name says, is simply the time that the process has spent in the ready queue, right? So the process is ready, but it's waiting for the scheduler's decision. So that time, that period of time is counted as the waiting time. So for P1, for example, it arrived at time 0, right? And it started running at time 0. So the waiting time for P1 is actually 0. It did not wait in the ready queue for any period of time. Now for P2, it arrived at time 1, right? And then it started running at time 6. So while P1 is executing, P2 was waiting, right, between time 1 and time 6, right? So P2 waited for 5 milliseconds, right? And same thing applies to P3. P3 arrived at time 3, but started running at time 9. So this is the waiting time of process P3. So this counts for 6 milliseconds, right? So these are the individual waiting times per process, right? Now, to calculate the average waiting time, all we have to do is average them. So the average waiting time will be 0 plus 5 plus 6 over 3. This is the average waiting time. Now, for the average turnaround time, we defined it as the total time that the process has spent in the system since arrival. So it is equal to the waiting time plus the burst time or the running time of that process, right? It makes sense, right? So the process will alternate between running, which is the burst time, and waiting in the ready queue, which is the waiting time, right? So the burst times are given in the workload, right? So you simply add now the waiting times, which we've just determined. So the individual turnaround time of P1 is 0 plus 6, right? And then this is the individual turnaround time of P2, which is 5, the waiting time of 5, plus the burst time of 3. And then same thing for the turnaround time of P3, and then we average them to get the average turnaround time of these three processes. So as we said, the idea of first come first serve is really a FIFO queue. It's really simple. You service the processes based on their arrival times. So in that's the main advantage. It's the simplicity, but it does have the disadvantage of yielding a large average waiting time, right, as well as a turnaround time. And it does have a second disadvantage, which we will talk about now. So in this second workload, right, so we have three processes. Here we don't mention the arrival time in this workload, therefore we can assume that all of these processes arrived at time 0 in this order: P1, then P2, then P3. So applying first come first serve would give us a Gantt chart. So this is called a Gantt chart, right? So the first one which arrived to the queue is P1. So P1 will run for 24 milliseconds, followed by P2, then P3. Both of them have a requirement of 3 milliseconds, right? So this will give us 27 milliseconds as an average waiting time and 17 milliseconds as an average. So this will give us 17 milliseconds, right, as an average waiting time. So these are individual waiting times per process, and this is the average, right? Now, if we change the order of arrival of these processes, right, assuming that they arrived in this order, P2, P3, P1, right? So P2 will run first for 3 milliseconds, P3 will run next for 3 milliseconds, and then P1 for the entire 24 milliseconds. So this will give us an average of only 3 milliseconds average waiting time compared to 17 milliseconds in the previous case. What did we change? We simply made the shorter processes go first, right? So this takes us to the second disadvantage of first come first serve, which is what we call the convoy effect, right? So because first come, first serve services processes based on their arrival, it doesn't look or it doesn't consider the burst time of the processes. If longer processes keep coming first, then shorter jobs or shorter processes will take a long time to run, right? So this will result in lower CPU and device utilization, which is the opposite of what we want to do. It's the opposite of what multi-programming and generally what operating systems mainly want to realize. Now coming to the second scheduling algorithm, which again still works for background or batch processes, and this time this is the shortest job first scheduling algorithm. So unlike first come first serve, SJF schedules or services the processes based on their burst time, right? Specifically based on their next CPU burst time, right? So it will always choose the smallest next CPU burst time process to run first, right? Now, if we have a tie, if two processes have exactly the same next CPU burst time, then we can use the order of arrival. We can use first come, first serve to break the tie. Now, again, this is a non-preemptive scheduling algorithm, meaning we are not allowed to preempt or to interrupt a process while running. So here is an example of application of the shortest job first scheduling algorithm. So we have this workload, 3 processes, and their corresponding arrival and burst times, right? So at time 0, again, this is the Gantt chart, Gantt. Right, so at time 0, process P1 arrives. So since at time 0, the queue has simply process P1, it's the only one, so we start running P1, right? So P1 starts running from 0 all the way to 6. It requires 6 milliseconds, right? And then we have P2 at time 1, arrived at time 1, and then P3 arrived at time 3. Right? So again, since this is a non-preemptive algorithm, so P1 will be allowed to finish executing, and we are going to simply add P2 and P3 to the tail of the queue, right? So once P1 is done executing, it will be removed from the queue. Now we have these 2 processes, which is P2 and P3. So now the algorithm will compare their next burst times, right? So P2 requires 3 milliseconds, while P3 only requires 2. Therefore, the algorithm will choose P3 to run next, right? And so at time 6, P3 will run, right, for 2 milliseconds, right? And then P2 is removed from the queue. We only have now P3. It will run next for 2 milliseconds, right? And now again, to calculate the average turnaround time, all we have to do is calculate the individual ones and average them. And to calculate individual turnaround times, we simply add individual waiting times plus their corresponding burst times, right? So P1 arrived at 0 and started executing at 0, so no waiting for P1, so it's 0, and the burst time is 6, so 0 plus 6. This is the turnaround time of P1. For P2, it arrived at time 1, but started executing at time 8. So it had waited for 7 milliseconds, right? Plus the burst time of 3. This is the turnaround time of P2. And then we do the same for P3, right? So P3 arrived at time 3 and started executing at time 6. So waited for 3 milliseconds plus the burst time of 2. So this will yield 5 milliseconds for the turnaround time of P3. And then we finally average them, and this will give us 7 milliseconds as the average turnaround time of these processes. Now remember I said that the shortest job first will pick the smallest, the process that has the smallest next burst time. So when I say next, that comes in the future, and since we do not know the future, then how would this algorithm be executed? So some implementations would actually estimate the next burst time of the process based on the last burst time of that process. Then comes the third scheduling algorithm, which also works for batch or background processes. It's called the shortest remaining time first. Okay, so this is actually simply a preemptive version of the shortest job first. Remember, shortest job first is non-preemptive. So once a process starts running, we're not allowed to interrupt it. Now, shortest remaining time is actually preemptive. Right? So the algorithm will make a decision whenever a new process arrives to the ready queue. It will actually compare their remaining times, right? How long each process still has to run and pick the shortest one. So let's take an example. So again, I have these three processes. This is their arrival time, and this is the corresponding burst time. So this is my queue. Initially, at time 0, I only have P1, right? And then at time 1, I have P2, and then at time 3, I have P3. So initially, since the queue only has one process, so P1 will be scheduled to start running. So it will run at time 0, and at time 1, the queue needs to be updated because a new process has arrived. So P2 will be added to the queue, right? Now the scheduler has to make a decision whether or not to interrupt the currently running process based on the remaining time. So we'll compare the remaining time of these two processes. So at time 1, P1 has already ran for 1 millisecond already. Therefore, at this point, it still needs to run for 5 milliseconds, right? 6 minus 1. Now, P2 at that point needs to run for 3 milliseconds. The shortest is P2, so P1 will be interrupted and P2 will start running because it has the shortest remaining time, right? So P2 will start running from 1, right, all the way to 3. At time 3, P3 arrived, right? Now we need again to compare the remaining time of these processes, right? This is P3. So at this point, P3 requires 2 milliseconds and P2 has already run for 2 milliseconds, right? So it only has 1 millisecond to go. Therefore, P2 has the shortest remaining time, so will be allowed to continue executing, right? So now P2 is finished, is terminated. What do we have now in the queue? We have P1 with a remaining time of 5, and we have P3 with a remaining time of 2. So P3 is the shortest, so will be allowed to execute between times 4 to 6. Now P3 is finished, it's terminated. Now P1 is allowed to execute for the remaining 5 milliseconds between 6 to 11. So now this time will be actually added and considered as the waiting time of these processes, right? So P1 had to wait between time 6 to 1, so it had to wait for 5 milliseconds. P2 didn't have to wait, so it started running as soon as it arrived. And P3 had to wait for 1 millisecond, right? So these are individual waiting times. We add up the individual burst times to give us individual turnaround times, and then we average everything.